Hello everybody, my name is Luke Poirier, and today I'll be talking about the physics of epidermal stem cells. So, what is my focus question? What are the principles of physics involved with epidermal stem cells? So, for an introduction, what are cells? Cells are the building blocks and the smallest functional unit of an organism. Inside there are many organelles which help the cell perform, and they also perform mitosis, which means they duplicate the genetic information and then duplicate themselves. Next, what are stem cells? Stem cells are cells that are just unspecialized, and they can become specialized due to different factors. As you can see, when we go down into more specializations of still stem cells, we get to the skin stem cell, which reside in the integumentary system, which I'll be talking about in a couple seconds. With stem cell fates. So, many different factors can affect stem cell fates. First is soluble factors, and then 3 physical factors, which are physical forces, extracellular matrix contact, and cell-cell contact. The ECM refers to just the environment that the cells reside in, that they can interact with. So after this one cell interacts, it has 4 different possible fates, 5. First is self-renewal, which means it revives itself. Differentiation, when the cell becomes specialized. Apoptosis, which means the cell kills itself. Migration, when the cell starts to move, which I'll also be explaining later. And metabolism, which just becomes a more complex cell, which I won't be explaining. Now, the integumentary system. So, there's 6 layers to it. First is the dermis, which is kind of below, but it does contain the dermal stem cells, which I'll be talking about their interactions with the basal cells. The basement membrane is just the block between the dermis and the epithelium. The basal layer, which are the stem cells of the skin, they're the only ones that perform mitosis and duplicate. The spinous layer, this is where the bulk of the skin comes from. The granular layer, which is the top of the skin cells, and then the stratum corneum, which is where all the dead cells reside and all the other types of materials that are on top of the skin. As well, what does actually skin do? It prevents trauma, water loss, temperature change, radiation, and infections. It also is a type of camouflage in nature. It allows to perceive the environment, and it is also decoration for social and reproductive behavior. So now I will talk about physics. First, pressure and Young's modulus. So, a study was done, and it said that you only need 10 to 20 newtons to break skin with a proper blade. So, the width of a blade is about 1/1000th of an inch, and this value for mathematical purposes, I won't say. So, with using pressure, which is force over area, to cut it, we can figure out that you need 3,937 kilopascals of pressure to pierce 10 centimeters of skin. So, now I'll talk about Young's modulus. So, what is Young's modulus? It refers to the stiffness of an elastic solid. It is proportional to stress, which, as you can see, stress is pressure, and it's also inversely proportional to strain. Stress is measured in pascals. Strain doesn't actually have a unit, it is measured with percentage. Young's modulus, because of this, is measured in pascals. As you can see, it is very similar to a law that we learned, which is Hooke's law, but just a different arrangement of variables. X is just delta L, which is just the change in length of the elastic solid. And then K refers to Young's modulus times the area of the surface over the length of the initial solid. Young's modulus only applies into the elastic behavior, just like Hooke's law, as we learned. And after the yield strength point, then there's the plastic behavior and the fracture point. So, continued. Skin is an elastic solid because it has 2 components. One is collagen. Collagen gives the structure to the skin, and elastin. Elastin gives the elasticity to the skin. The mean Young's modulus value for the human skin is 98.97 megapascals, but there are 3 difficulties with using Young's modulus to describe the skin. First, skin is not linear. It's 3-dimensional. It covers your whole body. And the only problem, a huge problem as well, is that there's no definite start or end to your skin since it covers your whole body. Second is that the plastic region is very small. After the yield strength point, it is very close to the fracture point if more force is applied to stretch the skin. And lastly, skin properties are very different in different areas of the body. As you know, skin at the bottom of your foot will be very different from the skin on top of your forehead. So, with a fingertip example, a study was done as well to find and discover the stress and strain properties and the Young's modulus of skin at the fingertip. So, a fingertip was put onto a glass surface like this, and it was dragged while a camera followed it, dots were put onto the ridges of the fingertip skin, because that was the most elevated surface of the fingertip. The acceleration was high at 0.16, and also just to clarify, point A is before the finger touches the surface, B is when it does touch the surface, and C is when the fingertip was actually moving across the glass surface. Since the acceleration was highest at P16, this means the frictional force was the largest at P16, so it allows us to find the proper strain of the fingertip. And we can explain this by using the second Newton's law, force equals mass times acceleration. After some rearranging, we find that the frictional force is equal to the constant 2.5 Newton force, F applied cos theta, because we're only talking about the tangential force across the plane, minus the mass times acceleration. The strain they discovered was 5.9% at P16. And now we'll try and discover the Young's modulus of the fingertip skin. So the average area of the fingertip, when pressed down into a glass surface, is 4.16 centimeters squared. So, with this previous information, the stress over strain, simplification, we find out that the Young's modulus of the fingertip skin is 101.858 kilopascals. What this means is that the stiffness of the skin at the fingertip is measured by the Young's modulus, and that gives 101.858 kilopascals. Now with this information, even though we found out before it was 5.9%, we can do some equations to find out that the stress is 6 kilopascals. So that means we need more than 6 kilopascals to get past the yield strength and get to the fracture point. We need more than 6 kilopascals of tangential stress to fracture or break the intercellular forces of the epidermal skin cells. Now, I'll talk about the physics of migration. So, in a cell, there's these fibers called actin. These fibers reach out of the cell, and they use their adhesive properties to stick to the extracellular matrix. Right here is just the extracellular matrix, it's just where the cells reside in. When they attach to a surface right here, this causes a lot of stress in the cell. Once the rear adhesive property releases, because with the knowledge of stress, the elastic solid wants to return to its original shape. This causes forward motion. Also, with more physics of it, there's actually drag force acting in the opposite direction as it's moving, because the cell does reside in a viscous surface, and it has a force acting on the other direction. Now I'll be talking about the physics of acute wound healing. So, an acute wound is when a physical force overcomes the intercellular forces of the epidermis. When this happens, the physical force splits the intercellular forces. The cells here, they lack the compression forces done by the other cells around it. Because of this, all the cells in this area become activated. Before I said that the basal layer is the only layer of skin that performs mitosis, but when this happens, the spinous and basal layer also perform mitosis. Now, when they perform this and they duplicate their cells, these cells migrate down to the wound bed and fill up the wound. As they're moving down, let's say a spinous cell right here duplicates and it moves to a basal cell. They become activated, as in they become actual stem cells. So a spinous cell, when it reaches the basal layer, will actually have the fate of a basal stem cell. As shown in the very beginning, a stem cell is not a single cell. It can be multiple different stages of cell, but it can still be determined to become more specialized. Now I'll be talking about chronic wounds. So it's a similar aspect, but the physical forces also breaks the wound bed. When this happens, the dermal cells lack the contact between the dermal cells and the wound bed, and this activates these layers of cells. When they activate, this means that they become highly reproductive, but they only have the fate of scar tissue. So it fills up this whole area, but it is not able to perform acute wound healing like the slide beforehand. And yeah, hair follicle develop, or sorry, as well with the chronic wound. There was a study in the mid-70s done by two scientists, and they found that the way that they can actually repair chronic wounds, such as burns or really deep wounds, is that they can actually graft skin from different parts of a person's body where basal stem cells reside, and they put it onto that tissue, epithelializing the skin, which is just making it proper skin again. There's only two problems with this. There's no hair. In that graft where that is, there will not be any hair follicle development or sweat glands, but it will be able to perform acute wound healing. As well, this has saved many lives since it's all been done since the mid-70s. It has actually really helped with lots of people who have had chronic wounds. I'm talking about the physics of hair development. So, when a hair follicle starts to be produced, this is done in like very young ages, the dermal cells are flowing through the dermis, and suddenly a dermal cell will attach to the base membrane. Now, they will perform, due to the actin fibers, they will perform a push force onto these basal cells. This causes the basal cells to expand and also perform mitosis, which then in turn enacts a push force onto the dermal cells. This then signals them to create a dermal papilla. A dermal papilla, as shown right here, is just the adhesive property at the bottom of a hair follicle and just signifies the bottom of a hair follicle. As these basal cells duplicate and perform mitosis, finally the dermal papilla also enacts a force onto the basal cells, signifying that they can turn into other certain cells such as the inside root sheath, and as well it signifies the actual start of the real growth and the real bulk of the hair follicle. Now with the hair cycle, so as you can see, hair actually grew, but there's also this little sac on the side. This happens when basal cells they make a sac, but they also they hold these other types of basal cells called epidermal stem cells. These are the basal cells, but the basal cells are just specialized to reside in the basal layer, while these stem cells are very similar, but they're just a little bit less unspecialized. During the cycle, they never degenerate, they only stay right here, and during the cycle, they proliferate and differentiate to go into different areas of the hair follicle to perform different duties. As well, if there's such a thing called like a chronic wound or an acute wound, and there's not enough mitosis going on, these stem cells can actually leave and go to the wound to actually help perform in the wound healing. So, now we'll be talking about the epidermal stem cells, but I also just want to talk about more of the physics about how physical forces affect stem cell differentiation. So, I'll be talking about cardiac stem cells. So, as we heard before in Sophie's presentation, that there's these two nodes, the synovial node and the atrioventricular node. So the S node gives a pulse of energy to the atrioventricular node, which disperses it through the heart. The cardiac cells in the heart, they have these excitable fibers that are able to conduct this energy. When the cardiac cells, they perform mitosis and they're unspecialized, they experience this current, and if they're not in that area, they won't experience the current. But when they do, that is their signal to differentiate into cardiac nodal cells to grow the path of the nodes. So, societal implications. As I said before, skin grafting. It saved many lives by having wounds. Another one is bone marrow transplants for people with leukemia. Leukemia is when a cancer grows inside somebody's bone marrow. In the bone marrow, the cancer grows, and after chemotherapy, they take out the bone marrow and replace it with other parts of bone marrow from the other parts of their body with multiple stem cells to regrow that bone marrow. And this has also saved many lives. There's other types of blood stem cells that are used to cure other cancers, but a very recognizable one is the umbilical cord stem cells. And why these are so important is that they do not have they're not recognizable by the receiver's immune system, and they also can't attack the receiver's immune system because they don't have the genetic information. Stem cells are fairly new technology. We're still discovering where the stem cells are, how they react to different factors. But in the future, definitely we can use them. Maybe use them to further our medical knowledge, and maybe even outside of the medical range. So in conclusion, physics was discovered in skin puncture, wound healing, and hair follicle growth, and the cycle. Also, I talked about the electrical force affecting stem cells and the societal implications on how stem cells are used in the medical field and how they're used in biology. So yeah, there's my presentation. Please remember excited.
Let's talk about how you connected with the alumna panel.
Oh, yes, sorry. I also talked about, I forget her.
Tanya.
Yeah, just Tanya. I forget
She's
her
from
last name.
Appleby. She's working in stem cells, so he connected with her.
She's working in stem cells. She really helped me on where to start off, because I knew that there was a lot of stem cells in the body, different types of ranges, but one that really affects physical forces very commonly